Hello everyone, my name is Brian Leclerc and this is my presentation for my poster on the development of cementitious materials for railroad crossties. For railroad crossties, a removal requires a 10-year life cycle. However, due to the nature of crossties, issues regarding the durability of the concrete can be accelerated from the loadings and impacts. The motivation of our research is to develop high-performance cementitious materials for the railroad crossties. We do this by focusing on three aspects: the structural performance of the concrete, the chemical resistance, and minimizing abrasion damage. AREMA has many quality control requirements that must be met. They will require 7,000 psi strength at 28 days and the 10-year service life. They also require resistances to alkali aggregate reactivity, delayed entringite formation, freeze and thaw, and corrosion. For our research, we expect to see 10,000 psi strength at only 7 days. We do this with a ternary cementitious matrix of cement, silica fume, and ground granulated blast furnace slag, as well as the use of non-metallic fiber. With this, we also expect to see a minimization of chemical diffusion that prevents alkali-silica reaction, delayed entringite formation, and the potential freeze and thaw. To start, we wanted to find the optimal amount and length of non-metallic fiber. The fiber we used is basalt fiber. We use basalt because it is resistant to corrosion, unlike metallic fibers. Both graphs right here in the top middle are fiber content versus compressive strength of the fiber reinforced concrete samples made. The one on the left is for the longer fiber, which is about 43 millimeters in length, and the right graph is the short 20 millimeter fibers. As you can see, we found 0.9% fiber optimal for the long fibers and 1.1% optimal for the short fibers. You can also see that the short fiber samples perform better across the board as opposed to the long fibers. This gave us the idea that about 1% of volume for short fibers is best for our purposes. Next, we wanted to optimize the ternary mix itself. We do this by changing the amount of slag percent in the mix. Both of these graphs show that 30 and 35% slag mixes were best after 28 days. It is worth noting that all the mixtures on these graphs were at least 8,000 psi after 7 days. This is well above the AREMA requirements, as AREMA is looking for 7,000 psi after 28 days. Next, in the top right corner, we wanted to evaluate the impact resistance of the samples based on their slag percentages. First, we developed an apparatus to impact the samples in a consistent way. This can be seen in the picture on the right. Basically, it is a long PVC tube that we drop an 18-pound metal bar down to hammer the sample that's underneath. After we did that, we had to develop a way to compare the samples and how well they resisted the hammer impact in a quantitative and qualitative way. To do this, we developed two methods. On the left, we have mass percent loss. This tracks how much of the concrete sample is still intact after each hammer drop. We do this until at least 20% of the sample is still intact. 20% of the sample is no longer intact. On the second graph, we have what we called hits until no rebound. We found that when dropping the hammer onto the samples, that after a certain point, the hammer stops rebounding back. For the first drops, before this point, the hammer hits the concrete sample and then bounces off noticeably, usually a few inches off of the sample. However, there's a point in every sample where instead of bouncing off the sample, the hammer hits the sample and sticks into it. This is also usually accompanied by like a large chunk flying off of the concrete. This hit where the hammer sticks into the concrete is what we call a no rebound hit. So in the second graph is how many hits each sample took before the first no rebound hit. Because after the first one, every hit after that until 20% mass loss is a no rebound hit. As you can see, both 30 and 35% slag mixes performed well in this testing as well. Lastly, we wanted to test the durability of the concrete to corrosion. As you can see, the engineered cementitious materials at the top performed much better than the basic concrete mix at the bottom. These pictures were both taken only 3 days in the accelerated corrosion chamber. For future research, The smoothest of concrete samples will be evaluated. This will be done with a light reflection sensor with the goal of smoothing out the concrete mixes. This is done with the goal of minimizing abrasion damage of the railroad crossties. That is all for my poster. Thank you for this opportunity and your time. Have a good day.